In this lecture we are going to start compressors. Okay, so what is compressor? Compressor is an open system device. Okay, and compressor are power consuming devices which converts mechanical energy into pressure energy. Okay, so compressors are going to be devices that converts mechanical energy into pressure energy with appreciable increase in density. Okay, it that means what does the compressor do? It compresses with the help of mechanical energy. Okay, it compresses the air or whatever the substance it is going to be. Okay, it is going to compress it by the action of mechanical energy, and it will compress it in a such a way that the volume is reducing, resulting in the increasing density, and due to the compression, the forceful compression, the pressure energy of it is getting raised. Okay, the pressure energy of it is getting raised. So such type of devices are known as compressors. Okay, now compressor is an open system device. Okay, now if you remember what is the work done for open system devices, then your formula goes like this: W open is equal to minus of integration of V into dP. Okay, so this was the formula for our open system. Okay, now there are five possible ways, or you can say five possible processes are there. Okay, so what are these processes? They are constant pressure, constant volume, then adiabatic, polytropic, and isothermal. Okay, there are five processes, but out of them you cannot go for the constant volume process, and you cannot go for the constant pressure process also. Okay, why? Because in the definition itself it is written that mechanical energy is converted into pressure energy. Okay, mechanical energy to mechanical energy to pressure energy. That means what? There should be a rise of pressure. Okay, there should be a rise of pressure during this process. Okay, so you cannot go for constant pressure process. If you go for constant pressure process during compressors, okay, then your the whole work would be in vain only. Okay, if you cannot rise the pressure by compressing any substance, then your complete work is in vain. Now the second thing is volume. Okay, constant volume process. Now you cannot go for constant volume process also. Why? Because in constant volume process there would be no increase in density. Okay, and if you do not decrease the volume, your density is not going to increase. Okay, so again the constant volume process, by rising the temperature you can increase the pressure, but its density is not going to increase. Okay, so whenever it cools down, it will come down to its original pressure only. Okay, so with the rise in temperature, whatever the pressure that can be increased by constant volume process, because constant volume process is like this. Okay, from 1 to 2 you can rise the pressure. Okay, you can rise the pressure. Okay, but that would be in vain, because if somehow the temperature comes down, the pressure will also come down, and it is not going to increase the density itself. Okay, so what are the remaining three processes? The remaining three processes are nothing but this is adiabatic process. Okay, from 1 to 2 adiabatic process, from 1 to 2 dash this is going to be polytropic process, and from 1 to 2 double dash is going to be isothermal process. Okay, now as we have seen, okay, in the earlier cases we have seen how the slopes are going to be. Okay, how the slopes are going to be in case of these processes: adiabatic, adiabatic, polytropic, and isothermal processes. Okay, in these cases this is the volume. Okay, this is going to be the volume from where we need to compress. This is the original volume. Now we need to compress. So now you can see, if you compress adiabatically, you can compress up to this volume. Okay, if you want to compress it to a different pressure, then you need to compress only up to this volume, and if you need to compress it in isothermal process, then you can compress up to this volume. Okay, so each time the volume is getting decreased. But here also there are something we need to mention. Okay, now you can see we have always said that for an open system work. In closed system work, what happens? Whatever the curve is there for closed system, okay, whatever the curve is there, if you project it in the volume axis, then whatever the area that is given, that is our work done by a closed process. closed system. Okay, now in case of open system, this is going to be an open system. Compressor is an open system. Okay, so I have also said that for open system, what is the total work done, or how can we find the total work done from the diagram? It can be the if you project the curve. Okay, if you project the curve of pressure axis, for closed system you project it in volume axis, and for open system it is going to be projected on the pressure axis. Okay, now if you project the slope on pressure axis, then whatever the area it is going to cover, okay, is gives us the work done by the open system. Okay, so from this diagram you can easily say, this is adiabatic process from 1 to 2, 1 to 2 dash is polytropic, 1 to 2 double dash is isothermal. Okay, so now you can easily say, if you project each and every curve on the pressure axis, then which process is going to have the lower work done, lower work consumed. Okay, or the amount of work interaction, which curve is going to give you the lowest amount of work interaction, that is only the 1 to 2 double dash. Okay, that means the isothermal process, 1 to 2 double dash is isothermal process. This is only going to give you the lowest amount, because if you go for 1 to 2 double dash, this much of area is going to increase, and if you want to increase it to adiabatic process, then this much of area again going to increase. Okay, so the lowest amount, this is compressor. Okay, so this is going to be work consuming device. That means the lowest amount of work that should be given to a compressor so that it can perform can only be possible in isothermal process. Okay, that means if you go for isothermal process, then only the work given to a compressor is going to be less. Okay, but we cannot go for isothermal process, as well as we cannot go for the adiabatic process also. Okay, why? Because practically isothermal process is very slow process. Okay, why is this slow process? Because if you give some heat, slight temperature difference would be there. Okay, now you will have to wait for the temperature to come. Okay, that slight increase in the temperature to come to its original position, then you are giving more heat. Okay, so that the temperature is again going to some some extent, then again you will wait to come take it to the original temperature. Okay, then after that you are going to give it, then also some more increase in temperature will be there, then you will wait for it to come down to the same temperature, and then like this your process will be going on. Okay, so it is going to a very slow process. Isothermal process is very slow process, because you are constantly reminding that you are not allowed to increase the temperature. Okay, so for this reason we have to add the heat slowly. Okay, so this is going to be a very slow process. And in case of adiabatic process, what happens? Adiabatic process is a very fast process. Okay, you have to do the process in such a short time that it does not get the time to interact with the surrounding. If there is interaction with the surrounding, there must be some heat interaction. Okay, there must be some heat interaction. So adiabatic process is a very fast process, and isothermal process is very slow process. Okay, so the only process that we are remaining with is going to be our polytropic process, and since this polytropic process lies between these two, okay, so this is neither very fast neither very slow. Okay, so only with polytropic process we can perform the compression process. Okay, so this is our three processes in PV diagram. Now coming to the TS diagram, or temperature entropy diagram. In this diagram, 1 to 2 is adiabatic process. 1 to 2 is adiabatic process. That means adiabatic processes are always isentropic process. So here, keeping the entropy same, 1 to 2 it is getting compressed. Okay, 1 to 2 dash. 1 to 2 dash is what? 1 to 2 dash is polytropic process. And 1 to 2 double dash is what? Constant temperature process, or isothermal process. Okay, so 1 to 2 double dash is constant temperature process. So this is parallel to the entropy axis, and this is isentropic, so this is going to be parallel to the temperature axis. Okay, and in between them there is going to be the polytropic process. Okay, so this is the basic layout of compressor. So after knowing that the only option we are staying with to analyze the compressor is going to be polytropic process. Now we are going to or we are going for the work done and analysis for the compressors. Now this is going to be a basic layout of the compressor, okay, reciprocating compressor. So this is reciprocating compressor, okay. So this is going to be the basic layout of reciprocating compressor, okay. Now it is constructed with two different parts. One is the piston cylinder arrangement. There must be one piston cylinder arrangement and there must be two valves, okay, and these two valves are going to be spring loaded, okay. Spring loaded means they are to open it and close it, they are connected with springs, okay. Now whenever there is a pressure difference between across these valves, then only these valves are going to open or close, okay. That means what, during suction, during the suction is going on, okay. Suction is what, this piston is going to go towards the outside of the cylinder, okay. The piston is going to go outside of the cylinder. That means what, there would be a suction created inside this, there would be a suction that would be created inside this cylinder, okay. Now after the suction creation, this is open to air, okay. This part is open to air, or if not air, you can say that whatever the gas we need to compress through this, okay, whatever the gas we need to compress to that, at what pressure that gas is kept, okay. Suppose we need to compress oxygen, okay, suppose we need to compress oxygen and this oxygen is kept in a cylinder and this oxygen has direct connection with this suction pipe of the compressor, okay. So whatever the P is given here, that would be the pressure outside this valve, okay, or this side of this valve, and inside this valve there would be one negative pressure. Why negative pressure? Because due to the movement of this piston, due to the movement of the piston towards the outside, what is going to happen, the whatever the air that has been, if there was any clearance volume, if there was any clearance volume, then whatever the air that was present inside the inside that clearance volume was expanding, okay. After expanding, what does happen when a gas expands? Its pressure is going to come down, okay. So after expanding to a certain limit, what is going to be there, its pressure is going to come down to so less pressure. That means one vacuum will be created here, or negative pressure or suction will be created here, okay. So due to this suction, this due to this negative pressure, what will happen, the spring will open, okay. Now whatever the work that has been done, negative work that has been done by the pressure inside this is going to be higher than the spring force, okay. It's going to be higher than the spring force, then only the valves are going to open. That means the main basic thing is these valves are going to work when there is some pressure difference across the valve, okay. So due to the suction, this air, whatever the air we need to compress is going to go inside this cylinder, okay. And during the backward stroke, now this is going to get closed, this valve is going to get closed, okay, during this backward stroke, okay. And what will happen, whatever the gas or air that has been present inside this cylinder is going to get compressed, okay. Now after compressing, the pressure is going to rise gradually, okay. Its pressure is going to rise gradually. So with the rise of pressure, this backward stroke is going to happen, okay, or with the backward stroke the pressure is going to rise. So after some time it will attain such a pressure, okay, it will attain such a pressure that would, and that work done by that pressure would be higher than the spring force that is operating this valve, okay. So the pressure inside would be so high that it will be more than the, or the force, okay, the force due to this pressure will be so high that this will overcome the spring force of this valve, okay. This will overcome the spring force of this valve. So this valve will open now, okay, and whatever the compressed gas was there, it will get discharged, okay, discharged, and it will be collected in some cylinder where we need to keep the compressed air, okay. So this discharge will be from the layout of the reciprocating compressor, okay. Discharge will be from the compressor, but it will be collected somewhere so that you can use it for later use, okay, so that we can use it later, okay. So this is going to be the reciprocating compressor working principle, okay. With the forward stroke, it is going to suck the air in which we suck the air or gas in which we need to compress, and due to the backward stroke it is going to compress it more, so that this valve opens, and with the discharge it is going to be collected to some other part where we can use this for later use, or we can directly use this air. We can, wherever we need the compressed air, we can directly use it. Suppose in case of refrigeration or in case of air conditioning. Okay, so you have seen the layout. After compressor it directly goes to the condenser for refrigeration. Okay, similarly for work producing cycles also, after compressor there is going to be heat addition process. Okay, either you can use it directly, whatever the discharge is there, the compressed air, we can use it directly, or we can store it so that we can use it later. Okay, now reciprocating compressor can compress up to 1000 bar. Okay, this reciprocating compressor can compress it up to 1000 bar, but the process would be very low because the volume delivered is going to be very less than. Okay, it's likely to be 9 meter cube per minute. Okay, per 1 minute time it is going to compress only 9 meter cube, but the pressure would be appreciably high. Okay, the pressure would be appreciably high. Okay, so this is going to be a reciprocating compressor, and now we will see what is the work input that is required for reciprocating compressors. So now we are going to see work input required by the compressor which is considered without clearance volume. Okay, so suppose there is a reciprocating compressor and there is no clearance volume. So in that case, what is going to be the total work that is required? Okay, so as we have said that this is going to be a cylinder with no clearance volume, that means the initial position before the suction, the volume is going to be at 0 position. Okay, before the suction starts. Okay, that means if there is no clearance volume, the piston will be just stuck to the cylinder head. That means the volume that has been enclosed by the cylinder and piston now is going to be complete 0. Okay, so it is going to start from 0. Okay, then the suction stroke happens. Okay, with the suction stroke, the volume that has been attained is whatever the total length by which the piston is going to go, and the cross sectional area of the cylinder. If you multiply this, then you are going to get the total volume that has been attained, okay, due to the suction. Okay, so this 4 to 1 is going to be nothing but the suction. Okay, or you can say 0 to 1 also. Okay, so 0 to 1 it is going to be a suction process. Okay, so during this suction process it is going to take certain volume of air. Suppose we are compressing air now. Okay, we are trying to compress air or air from the atmosphere. Okay, so during this suction, this much is the amount of volume that has been achieved. So let us say that this total volume is nothing but VA. Okay, or you can say volume of air. Okay, now after that from 1 to 2, what is happening? This is getting compressed. Okay, the compression stroke will be there. Okay, so half of it may be compression stroke. Okay, so half of it, or you can say due to up to some portion, it is going to be a compression stroke where it is going to get compressed polytropically. Okay, so up to 0.2, this polytropic process compression would be there. Okay, since this 0.2 is reached means what? Now the pressure inside the cylinder is so high that it is going to open the exit valve. Okay, after reaching 0.2, that means what? The compression, after the compression, the pressure inside is so high that it is going to open the exit valve, and after that 2 to 3, the discharge would be there. Okay, the discharge would be there. So discharge would be there means the volume again has come to 0.2. Okay, but up to the end of the discharge, the pressure was higher. Okay, this is going to be the pressure 2 is going to be the higher pressure. We are compressing it from pressure 1. Okay, from pressure 1 we are compressing it to pressure 2 by this compression stroke. Okay, so before the discharge of the whole thing, this is going to have a pressure of P2. Okay, and again when the suction starts, it is going to come with the atmospheric pressure of the, or you can say at whatever pressure the air is present, at that pressure the suction is going to take place again. Okay, and in this way it is going to take place. Now what is going to be the work done by an open system? Okay, what is going to be the work done by open system? Open system, why? Because compressor is going to be open system, because mass interaction would be there. Okay, so if you remember, for polytropic process, this was the value, or this was the formulation for work done by or work consumed by whatever. This is the work interaction formula was there for polytropic process. Okay, now this is generally P1 V1 minus P2 V2, but here it is P2 V2 minus P1 V1 because this is work input required. This is work input, not the work that has been given to us. Okay, so this is the amount of work which we are giving. So we are giving any work, that means this is going to be negative. So since it is negative, it is P2 V2 minus P1 V1 instead of P1 V1 minus P2 V2. Okay, now if you rewrite this, you are going to, what you are going to get, let us take P1 V1 common. Okay, so if you take P1 V1 common, what you are going to get, you are going to get P2 into V2 divided by P1 into V1. Okay, you are going to get this minus of 1. Okay, so this is going to be your expression. Okay, so now if you can see what is going to be the value of V2 by V1, what is going to be the value of V2 by V1. Now polytropic process is like this, P1 V1 to the power n is constant. Okay, so before compression this was the expression P1 V1 to the power n, and after compression this is going to be the expression P2 V2 to the power n. Okay, so from here if you need to find out what is going to be V2 by V1, okay, V2 divided by V1, so it would be P1 by P2 to the power 1 by n. Okay, this is going to be your value of V2 by V1. Okay, so if you write this, or if you replace this with the value we have got, it is going to be P2 by P1, and V2 by V1 is nothing but P1 by P2 to the power 1 by n. Okay, minus 1. Okay, now this is P1 by P2 to the power 1 by n, and this is P2 by P1. So we can also write this as P1 by P2 to the power minus 1. Okay, P2 by P1 we can write it as P1 by P2 whole to the power minus 1 also we can write. Okay, so now this P1 by P2 to the power minus 1 and P1 by P2 to the power 1 by 1 minus n is going to get simplified. Okay, so n by n minus 1, and P1, V1 means what? V1 is nothing but volume of air, you can say. Okay, in place of V1 you can write VA. Okay, so again from the ideal case equation, we have always known PV equals to M into R into T. Okay, so in place of P1 VA we can write MA into RT. MA is nothing but mass of air. Okay, MA is nothing but mass of air. Okay, now there is going to be P1 by P2. Okay, and the power is going to get added. So what would be there? 1 by n minus 1. This is minus 1 and this is 1 by n, so this is going to be the case minus 1. Okay, so this is the expression for what is going to be the work that is been required for a compressor without the clearance volume. Okay, if we are not considering the clearance volume, then this would be the case. So you can rewrite it as MA into R into T and P1 by P2. P1 by P2 then this is going to be your final formula for what is going to be the work input that is required by a compressor which is not having any clearance volume. Okay, so this is going to be the formula. Okay, so in some cases we are directly asked to find, this is the polytropic index, they will give you the value of n. Okay, they will give you the value of n, and they will say that we require to compress it from this pressure to this pressure. That means pressure 1 and pressure 2 are given, and they will say that we are going to compress air, and the mass would be given. Okay, so what are the things they will give? N they will give, P1 they will give, P2 they will give, and mass they will give, and the temperature also. Okay, so R you know for air what is going to be the R, and N it is given, P1 P2 given, T given, T there T would be T1. Okay, because since we are considering P1 VA, that means we are considering the pressure and volume at this point, so MA R T1 would be there. Okay, temperature at 0.1. Okay, mass of air is going to be constant. Okay, after the compression start, after the closing of the inlet valve, and so here the inlet valve closes. Okay, in this place the air inlet valve is going to get closed, okay, and up to 2 the exit valve is also getting closed, okay. After the point 2 the exit valve is going to get opened, okay. So from 1 to 2 the mass is going to be constant, that is the mass of total mass of air, okay. Only the volume is going to get decreased. R is there, T1 is there, okay. So you can write in place of this R, MA into R into T1. T1 is the temperature at this point, okay. Since we are taking the pressure and volume at point 1, so this would be the formula for work input for compressor without the clearance volume. So now we are going to see what is the work input required for a reciprocating compressor, but now it is with clearance volume, okay. So now we are going to consider the clearance volume, okay. Now up to point C it is going to be the clearance volume, okay. Point 3, okay, this is going to be the clearance volume, and this is going to be the suction, okay, or the swept volume. That means from here to here the piston is going to move, okay. From here to here the piston is going to move. Now what happens, this is going to be the clearance volume, okay. So this much is the clearance volume. That means what, in this clearance volume this much volume of air is already there, okay. This much air or this much volume of air is already present inside the cylinder before even the stroke starts, okay, or suction stroke starts. There is certain amount of air, okay, this much amount is there. Now, okay, from this point up to this point there is the air, so it is going to, when the suction stroke starts, okay, that means the swept volume is this, piston will start from this volume, okay. So piston will start from this volume. Before reaching point 4, the air inside, which is trapped inside the clearance volume, some air is trapped inside the clearance volume. So up to point 4 what is happening, the trapped air is going to expand, okay. That trapped air is going to expand. So with the expansion the pressure is now falling down, okay. So this, whatever the air, this VC amount of air or this VC volume of air is expanding up to volume 4, okay. This is expanding up to V4. So after expanding up to V4 what is happening, the pressure is the pressure inside the cylinder has now become negative, or you can say the suction pressure has created, okay, or the suction has been created. So after reaching point 4 it will go to point 1. So whatever the stroke is there from point 4 to 1, that is going to be the total suction, okay. There it is going to be the total suction. But in case of the previous part, okay, where we did not consider the clearance volume, the whole stroke was the volume of air, okay. During the whole stroke the air was going to go inside the cylinder, okay. Why? Because there was no air inside that cylinder so that it could expand, okay. So that it could expand, there was no air inside the cylinder because there was no clearance volume. Now here is one clearance volume. That means what, for this clearance volume it is expanding up to point 4, okay. So after reaching point 4, the remaining stroke is going to suck in the air. The remaining stroke is going to suck in the air. So what we can say, with the clearance volume, if we consider it with clearance volume, the volume of air that is sucked into the cylinder is going to be less, okay. So from point 4 when the stroke starts, this is going to be the volume of air, okay. Previously the volume of air was from here to here, okay, because of the absence of the air in clearance volume. Now up to point 4 it is going to expand, then only the suction will start. Then whatever the stroke is there, then whatever the volume that is covered by the stroke after point 4 is going to be the total volume of air, okay. So after that 1 to 2 it is going to get compressed again. After 1 to 2 it is going to get compressed again, okay. So this is going to get compressed polytropically, okay. Again 2 to 3 it is going to discharge, okay. It is going to get discharged. So discharge means what, it is going to volume 3 now, okay. It is going up to volume 3 now, okay. So after reaching volume 3, that means after reaching the clearance volume, whatever the air that has been present inside the cylinder, okay. So now this amount of clearance volume is filled with compressed air, okay. So what is happening, it is going to get compressed with, it is going to get whatever, that means after compression up to point 2, 2 to 3 is going to get discharged. Okay, so after discharging, what will happen? At some point the piston is going to stop. Okay, again, so at where it will stop? Whenever the volume inside this is going to become a clearance volume. Okay, whenever the remaining volume inside the cylinder is clearance volume, that means the piston is going to stop now. That means inside this clearance volume, now there would be some compressed gas that has been compressed in the previous stroke. Okay, that has been compressed in the previous stroke. That amount of compressed air is now trapped inside the clearance volume. Now it is going to be uh, trapped. Okay, again when the suction starts, again when the suction stroke starts, that compressed air is going to expand again. Okay, so that means what? When the suction stroke starts from 3 to 4, whatever the air, compressed air that has been trapped inside the cylinder is again going to expand now up to 0.4, and again after reaching 0.4 it is going to get the negative pressure. Then again the volume of air will go into the cylinder. So from this diagram, this is going to be the volume of air that has been taken, not unlike the previous one where the whole suction stroke was the volume of air. Okay, now what is going to be the work input required? Work input required is whatever the, now this compressed gas, okay, here up to here, after reaching this compressed gas is going to do some work. It is going to expand the cylinder. Okay, it is going to, since it is compressed, it is going to expand the cylinder by itself. Okay, up to some point. Okay, so that means what? That means what? There would be a compression work that has been required by during compression. Okay, 1 to 2 there is one work is required for compression minus WE. WE is what? The work that has been done by the compressed gas during the expansion. Okay, the work that is done by the compressed gas during expansion is going to be the WE. Okay, or work done during expansion, and this is going to be the work done during compression. Okay, so we have found out that work done by the compression is nothing but n by n minus 1 into P1 V1 P1 V1 P2 by P1. Now in previous one we have found out P1 by P2 to the power 1 minus n by n. Now we are writing P2 by P1, same thing. Okay, P2 by P1 to the power n minus 1 by n. If you reciprocate this, you have to add a minus. Okay, or you have to put a minus n. Okay, so by simplifying this, we have written it like this: work done by the compressor. Similarly, for expansion would be like this only. Okay, higher pressure by lower pressure. Here also it will be higher pressure by lower pressure, because P3 is higher, P4 is lower. Higher pressure by lower pressure to the power n minus 1 by n. Higher pressure by lower pressure to the power n minus 1 by n minus 1. Okay, so this is going to be the work done due to expansion. Okay, now in the previous case we have written this one as VA. That means what? Volume of air. Now we cannot write this because now volume 1 is not going to be VA. VA is only this much. Okay, VA is going to be what? Now here, from here, VA is going to be what? V1 minus V4 is going to be your VA. Okay, or volume of air. Okay, now if you are going to simplify this, from here you will know that P2 is equal to P3. Okay, P2 is equal to P3 because the discharge is going to happen in constant pressure process. Okay, 2 to 3 is going to be a constant pressure line, and it is also parallel to the volume axis, so this is going to, P2 is going to be P3. Okay, and again P4 is going to be equal to P1. Okay, P4 is going to be equal to P1. Okay, so now if you simplify this, what is going to happen? Now P2 is going to be equal to P3. Okay, so you can directly write P3 equals to P2. Okay, and again P1 is equal to P4, so you can directly write P4 is equal to P1. Okay, we are rewriting this. So from here you can see n minus 1 P2 by P1 to the power n minus 1 by n, and from here also this is going to get common. Okay, sorry, here one term is missing. Okay, the term would be n by n minus 1 into P4 V4. Okay, this term is missing here. So this would be the case. Okay, this would be the case. So this is similarly like this only. Okay, here also the before compression. Okay, so here the term should be the lower pressure and higher volume. Similarly here also it will be lower pressure and higher volume during the expansion. Okay, during the expansion lower pressure and higher volume, during the compression lower pressure and higher volume. Okay, so this was missed. Okay, so from here what you can say, this thing and this thing is going to get common now. Okay, so you can take this one as common, n by n minus 1. Okay, you are taking common n by n minus 1. And what is the other thing that is common? The other thing that is common is p2 by p1 to the power n minus 1 by n minus 1. Okay, these are the things that is common. Okay, and another thing that is common, now p4 is equal to what? P4 is equal to p1 again. Okay, so p1 is also common now from both these terms. Okay, from both these terms p1 is again common now, so you can also write p1. Okay, so after taking all of this common, what is remaining here? There is one v1 common and there is one v4. Okay, so there is one v1 and v4, so you can obviously write v1 minus v4. Okay, so these are the things that were common between these two. Okay, the remaining things were v1 minus v4. Okay, so from here you can again write n by n minus 1. Okay, now v1 minus v4 is what? v1 minus v4 is going to be your volume of air. Okay, so you can write p1 into volume of air. Okay, you can write p1 into volume of air, and what is going to be in the bracket? It is going to be p2 by p1 to the power n minus 1 by n minus 1. Okay, this is going to be the expression. So after that we can also rewrite this. So VA is what? Total volume of air, you can write it as MA into RT. P1 into VA, you can write MA into R into T. Okay, so after that, after writing that, what would be the final expression? The final expression would be n into n minus 1, MA into R into T1, here it would be T1, and this is going to be P2 by P1 to the power n minus 1 by n minus 1. So this is going to be the final expression for what is the work input required for compressor with the clearance volume. Okay, but if you see, it is going to be same as that of whatever the work input that was required for a cylinder, for a compressor which was with the clearance volume or without the clearance volume. Okay, so this expression is same for both with clearance volume and without clearance volume. So we can say that the clearance volume does not affect much in the whatever work that is required for us. Okay, whatever the work that is required for us to compress a certain amount of air, okay, a certain volume of air, the clearance volume does not play any role. Whether we take it with clearance volume or without clearance volume, this is the work input required is going to be same. Okay, so now we are going to see the volumetric efficiency. So what is going to be the volumetric efficiency? Volumetric efficiency is nothing but the ratio of volume of air. Okay, volume of air means what is the volume of air that has been sucked in into the cylinder to the swept volume. What is swept volume? Swept volume is the amount of volume that has been covered by the piston during its movement. That means the cross-sectional area of the piston has covered a total volume during its stroke length. That amount of volume is known as swept volume. Okay, now the ratio of the total amount of air sucked in by that swept volume is known as the volumetric efficiency. Now this is the diagram for a compressor where we have considered the clearance volume. Okay, now for a moment let us consider a cylinder where there is no clearance volume. Okay, so in such cases where there was no clearance volume, your suction used to start from here. Now your suction is going to start from here. Okay, so where there is no clearance volume, your suction used to start from here. Okay, and your clearance volume was 0. Okay, and whatever the suction volume was there, the total suction volume was covered with air. Okay, so in that case, that suction, this was the case of volumetric efficiency. But in that case, okay, in that case where we did not consider the clearance volume, that there VA is equal to VS. Okay, that total suction volume is going to take in that much amount of air only. Okay, so VA was equal to VS. So if you think that VS is going to give you 100%. Okay, So that means what? That is not possible. Okay, that is not at all possible. That means it is not possible to create a cylinder without a clearance volume. Okay, slightest amount of clearance volume would be there. Okay, and slightest amount of air would also be present there. Okay, would be trapped there. Okay, so volumetric efficiency can neither, or you can say that the compressor which you have considered without the clearance volume is not possible to it's not possible to construct. Okay, it's not possible to construct. So that means what? With the increase of the, now this is going to be 100%, but actually it is not 100%. That means what? In such in compressors like this, there is always some volume of air present. There is always some volume of air present. That means what? That volume of air is going to hamper the efficiency. Okay, with the increase of the clearance volume, there would be the decrease in the volumetric efficiency. That is the reason now we are considering the volumetric efficiency, where that cannot be, the volumetric efficiency cannot be 100%. Okay, now now let us take this case. Okay, in this case, what is going to be the volumetric efficiency? This is going to be VA by Vs. Okay, now VA is what? VA is nothing but V1 minus V4. Okay, VA is what? VA is nothing but V1 minus V4 is going to give you VA, and this is going to be Vs. Now if you see V1 is again divided into two parts, Vc and Vs. V1 is again divided into two parts, Vc and Vs. So in place of V1 you can write Vc plus Vs minus V4 divided by Vs. Okay, divided by Vs you can write. Now from this you can also write, now Vs by Vs is going to get cancelled out. Okay, plus Vc by Vs is there. Vc by Vs is there, and minus V4 by Vs is there. V4 by Vs is there. Okay, now this is known as, now C is known as the clearance ratio. Okay, which is the ratio of clearance volume divided by swept volume. This is known as our clearance ratio. Okay, so in this place we can write C. Okay, so in this place we can write C. That means what? We can write 1 plus C. Vc by Vs is known as the clearance volume. Okay, so from here we can also write it as Vc by Vc. So after writing Vc by Vs, that means if you can take this, Vc by Vs is what? Vc by Vs is nothing but C. Vc by Vs is nothing but C. So up to here it is written 1 plus C. Okay, so you can write minus of C now. Vc by Vs is going to be C. Okay, Vc by Vs is going to be C, and the remaining thing is what? V4 by Vc. So you can write here it as V4 by Vc. Okay, this Vc by Vs is going to give you C, and V4 by Vc is written here. Now you can see V3 and Vc are going to have same volume. Okay, that means amount of Vc and amount of V3 is going to be same. Okay, so in place of Vc we are writing V3. In place of Vc we are writing V3. Okay, so the expression is what? The expression is nothing but 1 plus C minus C into V4 by V3 is going to be your expression. Okay, now let us take this process. Okay, the expansion process from 3 to 4. Okay, so from here you can see that P4 to the power n is going to be equal to P3 V3 to the power n. Now we are going to find what is going to be the value of V4 by V3. So if you want to find V4 by V3, it is going to be n, and there will be P3 by P4. Okay, now again you can see that P3 and P2 are same. Okay, P3 and P2 are same. So in place of P3 you can write P2, and P4 and P1 are also same. P4 and P1 are also same. So in place of P4 you can write P1. Okay, so what is the final expression? You can write from here V4 by V3 is going to be equal to P2 by P1 to the power 1 by n. Okay, so this is the value of V4 by V3. Now let us put it there. Okay, so after putting it there, what would it be? 1 plus C minus C into P2 by P1, okay, to the power 1 by n. Okay, now from here you can take minus C common. Okay, so if you write it as 1 minus C, 1 minus C, the common thing would be P2 by P1 to the power 1 by n minus 1. This is going to be your expression for volumetric efficiency. Okay, this is going to be your expression for volumetric efficiency. Now from here you can see when the C increases, when the C is going to increase, that means C is going to increase and it is going to be, now C is increasing means this part is increasing and this part is increasing and it is subtracted from 1. Okay, this part is increasing and this is subtracting from 1. That means what? A large, if this increases, that means a large part of this will be get subtracted from 1. That means the final efficiency would decrease. It is same like when you have written 1 minus 0.5. This is going to give you a value of 0.5. But with the increase of C, let us say that with the increase of C, now that 0.5 is now increasing to 0.75. Okay, with the increase of C. So the final pressure will be 0.25. Final result would be 0.25. That means what? This thing is going to get decreased. Similarly, efficiency is going to get decreased. Okay. So that means what? C is increasing means what? C is increasing means this BC is increasing. Okay. BC is increasing means what? The clearance volume is increasing. Now with respect to a certain swept volume, if the clearance volume is increasing, okay, or you can say that the clearance volume is same but the swept volume is decreasing, okay, that means what? With the increase of the clearance volume or with the decrease of the swept volume, this C is going to increase, and if the C increases, that means the efficiency decreases. Okay, now if the swept volume is constant, that means what? With the increase of the clearance volume, which I have told earlier, we can see here, okay, that means we have proved here that with the increase of the clearance volume, the C is going to increase, and if C increases, then the efficiency is going to get decreased. The final thing is, if you increase the clearance volume, the efficiency would get hampered. Okay, and again, now let us say that C is going to be constant. C is constant, and your P1 is also fixed. P1 is also fixed. That means you are trying to compress a certain air or certain amount of air at certain pressure. So that means what? Your initial pressure is always getting constant. Okay, initial pressure is constant. Now it is up to you, up to which pressure you need to take it. Okay, up to which pressure you need to compress it. Okay, so you can take air at 1 bar. Okay, now you can compress it up to 5 bar, 6 bar, 7 bar also. Okay, this is up to you. So that means what? If your P1 is going to be constant, okay, P1 is constant, but you are constantly increasing the P2. Okay, P2, that means the desired pressure. P2 is what? P2 is nothing but the desired pressure. Okay, P2 is nothing but the desired pressure. Now if your desired pressure increases, this thing increases, that means what? This thing again gets increasing. Okay, this thing is again increasing, and this thing is increasing, and it is subtracting from 1, means the efficiency again getting decreased. That means what? That means what? Up to here, what is the conclusion that we have achieved? If the VC increases, efficiency decreases. If the P2 or the desired pressure increases, efficiency decreases. Okay, so this is the final thing which we have found out from here. Okay, so this is going to be the expression for volumetric efficiency. If the pressure 1, pressure 2 is given and the polytropic index is given, then you can easily find the volumetric efficiency, and these are the conditions which we have found out. And we have also seen that for a compressor where the clearance volume is not there, in such cases the volumetric efficiency, you can say this is going to be an ideal case where the efficiency is 100%, but that is impractical. That is not possible to construct a compressor where the clearance volume is not there. Okay.